Hey friends, generative AI is often talked about in terms that are kind of mystical and personifying, and really putting a lot of emphasis on chat as the main mode of interaction with it. What I discovered, and many others over the last year or so, is that when we treat AI as software, we can do so much with it. This video is based on a talk I've given at GenAI Zurich earlier this summer and on a tutorial I've given at Microsoft with my colleagues Alexandra Salieva and Sandeep Kulkarni. And I wanted to share it with you because I think it's a really nice, simple introduction to what treating GenAI as software means. So let's get right into it. So how did we get here? Well, we already had GPT-3 back in 2022, and there was not a lot of interest in it. And that's something that really surprised me when I realized how powerful it is. But I think because we were missing the instruction post training and the chat format, it was kind of difficult for people to imagine what you can do with LLMs. Then in 2023, ChatGPT happened and it took the world by storm. And now everyone only cared about chat. Chat is really powerful. It's kind of right now the killer app for large language models. It's not going anywhere. But what we're realizing is that LLMs can do so much more because LLMs are simply a new way of doing software. Why chat? Well, it was very intuitive for people to start chatting with AI because, of course, we all know how to chat. It's really easy to integrate a chat into some existing system or database. And it keeps the human in the loop, which is something we really find important working with AI, which can be quite unreliable and unpredictable. Unfortunately, chat isn't quite enough. The reason for it is, first of all, as a user experience, it leaves a lot to be desired, right? Like we don't really like spending the whole day chatting with AI. It can be exhausting. We like different ways of interaction, like clicking and looking, and chat doesn't really afford us this and doesn't let us form habits around using software. Chat doesn't allow us to integrate AI more tightly with our software system. It gives us this advantage of having a human in the loop, but then it can also be a disadvantage because it means that for everything we do, we have to wait for the human to do something and chat with AI. We don't get any of this promise of autonomy, which is a large part of what we're hoping to get from AI ultimately. And chat, we're discovering, isn't necessarily such a good business model, at least not for anyone other than the big providers of chat models. We've had so many startups complain with every new release of OpenAI that OpenAI killed their startup because they implemented some general feature like chat with your PDF or chat with your enterprise documents, and it turned out that these are things that are being baked into the main chat systems. So really the way to be successful with AI, regardless if you're like a startup or an enterprise, is to focus on your own unique domain-specific differentiated capabilities. So how do we treat AI as software? Well, it has kind of two parts. On the planning side, what we do is process mapping. It's just really useful to learn to view the world as a collection of well-defined processes, breaking down each process to the smallest discrete operations possible, and for every operation, determining the input and the output and the transformation between them. And then we can see that many of these operations can be achieved really well with generative AI. So I often joke that process mapping is the new prompt engineering, is the superpower that allows people to build with AI. As for the technical aspect of working with AI software, think of it just as a new kind of VM, right? If you think by analogy, the JVM is a VM where we kind of take Java code and translate it into instructions to the VM, which result in functions. An LLM is also kind of like a VM that takes prompts, instructions, and definitions in English and translate them into functions: input, transformation, output. It's just that the functions that are implemented by the LLM are very powerful. They do things that are hard or even impossible to do with traditional software, and they tend to be quite easy to program. What really helps is using structured input and output to help bridge between the world of traditional software, which is orderly and well defined, and this slightly unpredictable and hard to control world of AI. So you just use a clear schema, clear validation rules, guardrails, and you have a way to harness AI. When you do that, you get several advantages. One of them is just deep integration with your system, your product, your process, your user experience. You can now build a rich system that uses AI at its back, but presents itself to the user in the most useful way to it. And you can even get some limited autonomy where it's appropriate. Securing AI system can be really difficult again because they are unpredictable, they are non-deterministic. But when we break things down to discrete operations, we can exercise much tighter control and add guardrails that are specific for each operation. So, really great, really important for security. And also for reliability, because when we break things down, we can understand and reason about every aspect of our application just as we would with any piece of software. And we can test it and evaluate it and observe it in operation. Finally, breaking down everything to operations gives us a lot more choice because we can use the model with the best trade-offs of cost, performance, capabilities, licensing, customization, fine-tuning when we need that. Many operations can be performed with small models like 5.3 or GPT Mini or Mistral or the Llamas or the Gemmas and get us really great performance at good speed and cost, while some other operations we want the strong intelligence of frontier models. LLMs are stateless, so there's really no reason to use the same LLM for everything. We have a lot of choice. And evaluating which LLM to use is a lot easier when we do it on a per operation basis. Alright, so on to the tutorial part of this video, where the fun begins. This tutorial will explore several really simple examples of using an LLM as software for different tasks. We'll be using GPT-4o for everything just to keep things simple, but many of these examples can work just as well with even simpler models. To do this, we'll be relying on defining schemas with Pydantic, which is a great Python library for defining schemas and validation rules. And we'll get the LLM to use them using Instructor, which is a great library by Jason Liu that patches the OpenAI API to always return results with the schema specified by the Pydantic model. As you'll see, we'll be doing very little prompting. Almost all of the power will come from the schema definitions. These examples are small and simple, but if you master this approach, you'll see that you can do many great things with LLMs. One note, this tutorial is in Python using a Jupyter notebook. If you don't speak Python, Instructor is available for many other languages, and you'll be able to translate what you learn. And even if you don't do much programming, I think that following this will give you a sense of what's possible when we treat AI as software. So to set things up, you'll need a deployment of GPT-4o. This can be just the OpenAI endpoint with your API key, or a deployment on Azure OpenAI, or perhaps GitHub models. You can find a tutorial on my GitHub at LLMs Beyond Chat, so just clone it, copy that .env template file to your own .env and configure it either with an API key or if you're using Azure or GitHub with endpoint and model name. You'll find two versions of the notebook. One of them is the complete ones with all the solutions, and another one with the solutions redacted. So if you'd like to kind of fill in the blanks and do a proper tutorial experience, you can use this one, pause when we go over the solutions, and try your hand at it. Let's see what we need to set up before we get started. So we are calling Instructor to patch the OpenAI client and return a client that is identical, except that it also accepts a response model parameter, which allows us to define the schema for every call. We define here this LLM function, which just kind of as a shortcut lets us give the function call a response model, a system message, and a user message, and temperature and max tokens when we need to customize that. As you'll see, this is a very convenient way to repeat this pattern of just calling with a system message for instruction, user message for the parameters, the data we pass to the function, and the response model for the function definition. The first example will be working with text and do some translations. If you look at the model, you'll see that it's translated into a JSON schema, and we'll inspect it. And you'll see that we can complete the task of translating from one language to other with very little prompting, just by giving a good definition. We'll be using the list and enum types of Python for a more complex structure, and we'll be using this convention that you'll see us repeating again and again in this tutorial, but it's really just a convention to use the system message for kind of the function definition and the user prompt for the input. So what we see here is we have some text in German. We define the schema of a translated string. It has a field input language, that's the language of the original text, and we ask for it to be in a 2-letter language code, and the translation, that's another string. When we print the schema, we'll see that this very neat little Python class translates into quite a lot of JSON schema, so it's nice that we don't have to type it ourselves. And the call to the LLM here, as you can see, is very simple. We're passing translated string as the definition of the response, detect the language of the original text and translate it into English as the instruction, and then the German text. The result, as you can see, is of course correct. This is a very simple task for a powerful LLM like GPT-4o. And the schema, as you can see, is a lot. So we're just looking at it here so that we get a feel for it, but we never have to type it. We'll be using Pydantic for all of these. Let's try now something a bit more complex. So this time we'll take the text in English and we'll translate it to several languages at once. We have here a Python enum with several language codes, German, French, Italian, Spanish, and Hebrew. And we have, again, a model that's defining a language, the language code, and the translation, but also another model that has a list of such translations. When you see the schema, it's already getting quite long, but really just expressing this idea. And we'll call the LLM passing the translations, the one that has a list of translations, as the response model. And the request translate the user-provided text into the following languages. Then we'll use JSON dump sets, so to dump all the languages we have in the enum. So nice way to provide structured input and not just output. We'll then provide the English text as the user prompt, the input to the function, and we'll set the temperature a bit higher because for a creative task like translation, it makes sense to give the LLM a bit more freedom. So the result you see, the schema here redacted, is already quite long, but it contains all the information that we have in these nice Pydantic models. And the result, pretty much what we expect. The LLM followed their instructions and provided translations to all these different languages. A similar task to translation is when we can call normalization. So that's kind of translating within the same language from one style to another. Not a big difference here, and you'll know already how to do this. We will have an input text that we want to sort of reformat or rephrase in different styles. We have a text style enum with different styles or registers of text, like formal, informal, casual, and so on. Normalized text for containing the style in the translation, and normalized texts with a list of such normalizations. And again, we'll call with instruction and with a JSON dump of the different styles we have in the enum, and the result, pretty much what we expect. GPT-4o does a really nice job here. One really cool thing we can do with LLMs is parsing unstructured data. There's tons of data that is kind of hiding within long prose and all kind of complicated text, and in fact, even in images and other modalities. What we'll do here is we'll parse an address and then some addresses. If you look at this example, we're not doing any prompting at all. Don't expect that to work with every task you do, but I just thought it's really nice to see that the LLM is pretty smart and can figure out just from the definition what we're trying to do here. So we have an address as a string, and we have a base model defining different fields that should be for each address, and we just call the LLM passing the model for the definition of the response and the address, and it does exactly what you'd expect. We get back a JSON with all the fields filled in as we should expect. The same thing we can do with multiple addresses, this time really in this sprawling text of all kind of addresses that I supposedly visited in my travels. We'll use the same address info model that we used above, but we'll do this time in a list of them because we will have many addresses. We call the LLM with the addresses model as the response model. Pretty clear and simple instruction, return all the addresses in the user provided text, the input text, and we get all the addresses parsed very nicely. So really powerful technique you can use for taking all sorts of unstructured data you have and translating it into something that already looks like a record in normal software. And that's something that's very widely applicable. Another cool example of working with unstructured data is one of building a knowledge graph. This is like an example that I picked up from the instructor documentation, which I think is just absolutely brilliant because it shows you how much intelligence we get in a strong LLM and what we can do with it. So if you remember, we defined a visualize graph function in the beginning just to help us look at the results, and now we'll be using it. We have some input text with all kind of random facts about the world, about different products, and some of them are edible, and some of them are newspapers, and so on. And we'll define a structure for a graph with nodes and edges, and a knowledge graph that has a list of nodes and a list of edges. And then just this very simple call to the LLM, use the knowledge graph as the response model, format the information in the user provided text as knowledge graph, and providing this text. So as you can see, no problem for the LLM. A lot of it is smarts that are kind of baked into the LLM, understanding what is a knowledge graph, how does it work, why having access to a list of nodes and a list of edges and them referencing each other correctly is going to help us build such a graph. But really nice, really powerful, and really great way to take unstructured data and build a complex structure that we can later on use to query and traverse. And one more example like this is that of parsing a grammar tree. So this is something that used to be kind of computational linguistics 101. Um, Taking a sentence, which is like a string of words one after the other, and parsing it into this nice descriptive tree structure of a verb phrase, a noun phrase, and a preposition phrase that tack onto them. And it's kind of a nested structure. And this used to be a real problem that people put a lot of effort into parsing, not just such simple sentences, but also more complex ones. And turns out LLM does it really, really easily just with the structure. So we provide here the canonical sentence, the quick brown fox jumps over the lazy dog, and models just for the tree structure. So a noun phrase that has a determiner and an adjective and a noun, preposition phrase that will have a preposition and noun, and a verb phrase that will have a noun phrase embedded in it, a verb and a preposition phrase. And then we'll ask the LLM, with this structure as a response model, parse the user provided sentence into a simple grammar tree. And it does that very well with a nested structure and all. So really nice demonstration of just how smart the LLM is and how it can help us move from unstructured data to something that's structured. Data is something you can never have enough of, right? Especially when you work on machine learning or just general data science projects. And it used to be really difficult to get your hands on data. LLMs are great at generating as much data as we want on demand for training, for evaluation, for all kinds of projects like this. And so you can just control what it is you want to get there and generate as much data as you need. In this example, let's say that we're generating data for a sentiment analysis project. We want to generate a sentiment and a rating. In this case, we're calling the LLM, asking it to generate a food review with a rating between 1 and 5, giving it a bit of temperature because it's now going to be generating some text. And as you can see, very nice, not very good review, and rating is indeed 1. And we can do the same with multiple outputs to generate just as much data as we need. And so in this case, we have an enum for rating from 1 stars to 5 stars, a sentiment model with a sentiment and the rating, and a list of such sentiments because we'll want to generate multiple. In fact, we'll generate 10 of them. We also call the LLM with synthetic sentiments, the list of sentiments as the response model, with a request generate n, where n equals 10 food reviews, and so on. And with the rating, dumping the JSON so that we have all the possibilities available, even though that will be also in the schema, giving it a bit of a temperature, and we get the result as we'd expect, 10, 2 of each, of varying degrees of rating, and as you can see, the text fits what we'd expect. One thing we'd want to do with AI is decision making. Just as in normal software we have if-then conditionals, an ability to branch and go this way or the other, with AI we'll want to delegate decision making to the AI in some cases. Sentiment analysis is one such example, right? Because we are looking at a piece of text and making a decision how to judge it. Is it positive sentiment or negative? And the LLM can also exhibit some kind of like a self-reflection effect when it can estimate its own confidence. And so this is a nice example of this. We have a few sample texts, a sentiment model, enum with positive, negative, neutral, a sentiment analysis model with this enum, and a confidence float. And what we'll do is for each text, we'll ask the LLM to analyze the sentiment and then provide also the confidence, which is really just part of the definition. And it does it pretty well, right? It definitely gets the sentiment correctly. It gives different confidence depending on how clear it is that it's really this sentiment, and I think this adds up. So, pretty powerful tool for decision making. Another example of decision making is classification, right? So, like tagging or dividing things into different groups. What we want to do here is kind of look at information we have that is unstructured, just in text, and use the knowledge the model has already to make decisions on how to categorize it. Not that this works for things where we really can rely on the model to have this knowledge. In other cases, or if we're using a smaller model, we might need to provide a lot more help in the prompting on what's possible. But in this case, we'll just be relying on what's already there in the LLM. And so we have a bunch of items. This could be, I guess, books or something like this, um, that sort of describe different things from potentially different categories. We'll define a bunch of potential tags like literature or science or sports or health. And then a taggable item model and taggable items, a list of them. And we'll ask the LLM for each item to kind of specify the title, subtitle, and give it a few tags out of this enum. And as you can see, it does a very decent job at this. If you review the titles and the subtitles and then look at the tags the LLM assigned to them, they make a lot of sense, as you would expect. Clustering is another kind of decision making, right? When we decide to put things in different groups. This is something that used to be done using predictive machine learning, often with a challenge that even if predictive machine learning model can cluster things well, it is really hard to understand why it's doing that, right? The explainability is missing. That's kind of an advantage we get with delegating this task to an LLM. So we'll use the same items from before that we already tagged, and we'll try to get the LLM to cluster them. We have a model for a taggable items cluster. So that's a cluster with a title and several items. The title is the explainability here, right? Because giving the cluster a title means that the LLM knows what it's all about, why it's putting things together. And we'll have a list of such clusters. We'll ask the LLM to create num clusters, where num clusters equals 5, with a JSON dump of the items we have from the previous exercise, and then look at the results. That's pretty neat, right? So the LLM invented a title for each cluster that makes perfect sense if you look at the items that have been included in this cluster. And now we have clustering plus explainability. Finally, planning and interacting with the world. So there's tons of talk about agents and agentic behavior, which I'm not sure I completely understand. But I think the elements of it are really, again, elements of software. One of them is planning, deciding what to do in sequence. This is something we do in computer programs all the time, but we can delegate this to the LLM and get some dynamism there. In this example, we created an enum of many different actions, sort of the kind of things that a human or perhaps a humanoid robot would be taking as they go about their day. And we'll then pick up these three different activities: waking up and going to work, winding down, and so on, and have an action sequence model, so just a list of actions. And we'll then ask the LLM, give us a result with action sequence as a response model, and generate a sequence of actions for the user provided activity, which will pass as the user prompt. And as you can see, the LLM does a really decent job here, kind of planning the day or planning the activity for this human or humanoid. Again, this obviously relies on a lot of knowledge that is baked into the LLM. It wouldn't work for something very specific. There, we would have to provide a lot more support in the prompting with what's possible. Still, it's a nice example of how planning works as part of this kind of agentic system. And for our last example, we'll play a game. So here we really have things that look a bit like agents. We'll implement tic-tac-toe. I know it's not very difficult to implement tic-tac-toe in normal programming, but it does make for a really simple example because we'll delegate all the complexity to the LLM and it will do everything itself. And to be fair, LLMs have been shown to play chess and other games very well. What we'll do is we'll have two agents, right, the two players working, playing together tic-tac-toe. We'll have a board, which is how they maintain state. So we have here a tic-tac-toe move. That's just the coordinates for making a move. A strategy. So these are different strategies that the LLM can use. It can be an optimal strategy, the one that's sure to win. Random, just putting something somewhere, or the next free slot, which is definitely not optimal. Tic-tac-toe winner is an enum just for the state of the game, so it could be that X is winning or O, or it could be a tie, or it could be that there's not yet a winner, the game is ongoing and there are still moves to make. And finally, a model for returning this winner. We'll have a board object. So the board is really the state of the world in which these two agents interact. This class is very simple. It just kind of draws the matrix with the tic-tac-toe board and has a check status function. And the check status function is implemented completely using the LLM, right? So it returns the tic-tac-toe status object and has pretty simple instructions: check the status, determine if there's a winner or tie or it's still ongoing. We provide a dump of the board, so the sort of the printout of the tic-tac-toe board as the user, and we'll limit the number of tokens. That's because the LLM like GPT-4o would get quite chatty if we allow it, and it's actually not necessary here. And so we'll save a lot of tokens by telling it, just get to the point, tell us what's the current status. And we'll implement the player. Again, this is our agent. It has a role, either X or O, and a strategy. And it has a turn method, so that's when it needs to make a move. It's very simple. It's implemented using the LLM, so it returns a tic-tac-toe move, and we're telling it you're the tic-tac-toe player, your role is X or O, it's now your turn. Use this strategy, look at the board, announce your move. And we'll provide the board as the user input so that it can decide on the move. And once we get the result, we'll pass the message to the board, make this move. And now we can let it go. So we'll create a board, two players, and then we'll loop, letting each player make a move in its turn until there is a winner. And when we run it, we'll see that it all works just perfectly. In this case, X is always going to be the winner because we gave it the optimal strategy, but you can play with it and try different combinations. So, as you can see, AI really is just software. And when we treat it like software, we can use everything we already know about working with software to achieve really great results. LLMs are just VMs that define functions not with code but with language. And when we use structured input and output, we can connect the very orderly and sensible world of software that we already know to the very powerful world of artificial intelligence. If you like that, some things you can follow up with is try these examples or similar ones with other LLMs, for example, small ones like 5.3 or GPT Mini, or perhaps open models like Llama or Mixtral. Identify some more complex tasks that you can achieve with this approach. Break them down, figure out how to implement each with an LLM and how to test it, and how much can you rely on the definition? Where will you need to invest a little bit more in prompting and giving clear directions to the LLM? And thinking how to evaluate and integrate these solutions into your software system. Hope this was enjoyable. I had a lot of fun. Until the next time, bye.